Bismillahirrahmanirrahim. How are you, students? Today we will study damped oscillation and different types of damped oscillation. Some of the topics is missing in your book, but we always got questions regarding to these topics, so I will do it for you people. So damping. Today we will study damping. Damping. So first we will study critical damping. Critical damping is when the system returns to its equilibrium position in the shortest possible time without any oscillation. For example, this is a pendulum. When it is displaced from its equilibrium position, it vibrates, it oscillates. So it's a critical damping. It's a critical damping. If it's not a critical damping, it's light damping. So if it keep its oscillation, it is critical light damping. But if it is displaced to this position, from this position, it is displaced to this position and it returns to its position without oscillation, then it is called critical damping. Example is instruments such as speed meter are critical damping. So when a car accelerates, the speed meter quickly changes and it does not oscillate not confuse the driver. So if you look to the speed meter, if you accelerate the car, it will the speed meter will represents the exact speed. It will not oscillate. If you are moving with 100 kilometer per hour, it will be on 100 kilometer per hour. It will not oscillate about 100. Sometimes it's got to jump to 110 and to 90 or jump to 90. It will not oscillate around. It will not keep its vibratory motion. Not oscillate. It will not oscillate. It will be exactly at the point or at the speed at which the car is moving. The shock absorber on a car is critical damping. Shock absorber is the example of critical damping. The suspension of the vehicle and so resists the setting up of vibration which could make control difficult or cause damages. So shock absorber are also the example of critical damping. So if you look, critical damping is if the body returns to its equilibrium position without oscillation. Examples are speed meter of a car, shock absorber are the examples of a critical damping. Are the example of a critical damping. Now, heavy damping. The system returns to equilibrium position very slowly without any oscillation. Heavy damping occurs when the resistive forces exceed those of critical damping. So, in critical damping, there is a little bit chance, might be, there is no oscillation, but might be a mild oscillation, a mild. In heavy damping, there is no chance. Do you ever see one of those things above a door? Sometimes there is a damper over a door. How slowly the door swings shut without any oscillation depends on how strong the damper is. In most cases, the damper used on a door is heavy damper and it slowly closes the doors with no oscillation, meaning the doors does not swing back and forth. If it slowly return to its equilibrium position, slowly, slowly return, it is heavy damping. But sometimes the door oscillates. That is critical light damping. And critical damping is when it returns to its original positions quickly, without oscillation. Critical damping, return to its equilibrium position quickly without oscillation. Heavy damping, return to its equilibrium position slowly. Light damping, define, defines, defined oscillations are observed, but the amplitude of oscillation is reduced gradually with time. Imagine the same door with a light damper. The light damper will allow the door to swing back and forth, the swing decreasing in momentum until the door slowly comes to a stop. If there is oscillation, for example, simple pendulum is an example of light damping. So heavy damping returns slowly to its equilibrium position without oscillation. Critical damping and light damping is a type of motion in which the body returns to its original position without oscillation. Without oscillation, light damping return critical damping return quickly to its equilibrium position. Heavy damping returns slowly to its equilibrium position, and light damping oscillate about its mean position. Listen again. Critical damping, heavy damping, light damping. Critical damping return to its equilibrium position quickly without oscillation. Without oscillation. Heavy damping return to its equilibrium position slowly without oscillation. Light damping return to its equilibrium position but keep oscillating about its equilibrium position. Now, waves motion. Waves motion is the mechanism by which disturbance is transferred from one place to another place. If you if this is your room and you switch on music loudly, switch on music loudly. If your brother or sister is sleeping in the other room, she will hear the music and disturbance is transferred from your room to this room. Music is actually the vibration, pleasing sound. So, in your room, you create sound, you produce disturbance, and that disturbance is transferred to this room. So, this mechanism by which disturbance is transferred from one room to the other room or from one place to the other place is called wave motion. So wave motion is the mechanism by which disturbances travel from one place to another place. Propagation of disturbance, that is deviation from a state of rest to from state of rest or equilibrium, from place to place in a regular and organized way. So when disturbance is created in one room and it is transferred to the other room from one place to the other place, this mechanism by which disturbances travel, disturbances transfer is called wave motion. Waves have two types, mechanical waves, electromagnetic waves. In your book, there are two types of waves, mechanical waves, electromagnetic waves. But there is a third type also, matter waves. Matter waves. Mechanical waves is divided into two types, longitudinal waves, transverse waves. The example of transverse waves is water waves, and sound waves are the example of longitudinal waves. Electromagnetic waves, light, microwaves, infrared waves, X-rays, ultraviolet rays, radio waves, mobile waves, any type of waves, X-ray, these are electromagnetic waves. But here we will study mechanical waves. Electromagnetic waves does not need medium for the propagation. You studied these in class 7, does not need medium path of propagation, medium dependent, medium dependent waves. Mechanical waves cannot travel through vacuum. These are There are two basic types of wave motion for mechanical waves: longitudinal waves and transverse waves. Longitudinal waves. The longitudinal In a longitudinal wave, the particle displaced is parallel to the direction of wave motion, to direction of wave propagation. If wave is traveling in this direction, wave motion, the particle will vibrate either in this direction or will propagate in this direction, parallel or anti-parallel. The animation at right shows a I will show the animation to you people and you will see. Now, you read this, I will explain the animation. Now, if you look to the diagram, this particle is moving in this direction. This motion, the medium motion is also in this direction. So it's a longitudinal waves in which the motion of the particles is parallel to the direction of propagation of waves. Direction of propagation of waves is this one. Wave is propagating in this direction. Wave is traveling in this direction. This is wave motion. This is wave. Black one. This is wave motion. This is wave motion. This is the motion of the particle. Motion of the particle. So this represents wave motion, the black one, and this represents particle motion. So the particle motion and the wave motion both are parallel. Particle motion is this one. Wave motion is also this one. Both are in same direction. So it's a longitudinal waves. Sound waves is the example of sound waves. Is the natural example of longitudinal waves. Transverse waves. In a transverse waves, the particle is perpendicular to direction of wave propagation. I will show the animation. The S waves mean secondary waves. This is an example of transverse waves. For example, if this is a string and it is fixed here and you give up and down jerk, it will start vibration like this. So the particle motion is upward and downward, but disturbance is transfer in this direction. So direction of propagation of wave is this one. Particle is vibrating in upward direction or in downward direction. So this type of waves is called transverse waves. You will check the animation now. Here the particle is vibrating up and down, and disturbance is transfer in this direction. This is the transverse waves. In longitudinal waves, the direction of propagation of waves and the particle vibrate parallel to each other. So when they vibrate parallel to each other, they are called longitudinal waves. In the direction of propagation of wave, direction of propagation of wave and direction of the direction of vibration of the particles are parallel, and then it is called longitudinal. When the particle vibrate perpendicular to a direction of propagation of waves, then it is called longitudinal transverse waves. This is the next example you can see. Same but with small size. You can check. Particles move up and down on its own position, and disturbance is transferred to the edge. This is different terms, we will explain different terms related to simple harmonic motion. This region is called crest, and this region is called trough. This is called crest. This is the starting of trough. So it's vibrate up and down, and disturbance is transferred in this direction. So it is called transverse waves. This region is called trough. This is called crest. Crest, trough, wavelength. This and this, because after this the wave repeat itself. So a scar transfer, a scar wavelength. This region is called compression. This region is called rarefaction. Compression, rarefaction. Here the the this rings are close to each other. They are dense. They are closely packed. Here they are further from each other. So this is called compression. This is called rarefaction. So when the particles of the medium are close to each other, then it is called compression. And when they are further from each other, it is called rarefaction. Waves, you studied different types of waves now. And you also studied this one, so revision. Wave is the, what is wave? Wave is energy carrier. Waves are energy carrier. Waves are disturbance in a medium. Mechanical waves, those waves which need a material medium for its propagation is called mechanical waves. Electromagnetic waves, which does not require medium for its propagation. Waves is energy carrier. Waves carries energy. Wave is a common term for a number of different ways in which energy is transferred. In electromagnetic wave, energy is transferred through vibration of electric and magnetic field. Do memorize this. Electromagnetic waves carry energy, or energy is transferred through electromagnetic waves by the vibration of electric and magnetic field. Sound waves, in sound waves, energy is transferred through vibration of air particles or particles of a solid through which the sound travels. In water waves, energy is transferred through vibration of the particle. Wave transfer energy, not mass. Waves transfer energy, not mass. If waves are energy carrier, people will sit in the sun, will absorb energy, and their weight or mass will be changed. Waves are energy carrier. It transfer energy from one place to another place. In short words, the meaning of my example is waves are energy carrier, and energy is not matter. Energy is not matter. Waves is energy carrier. If you take a tub, a tub of water, full of water, and you create disturbance in the midpoint, it will transport to the edges. So disturbance is created at the midpoint and it is transferred to the edge. But if you put an object in the midpoint, it will vibrate up and down. It will keep up its up and down motion, but will not travel to the edge, but will not leave its position. So water waves also transfer energy from one place to another place is explained. Dip one end of pencil into a tub of water and move it up and down vertically. Water waves will be produced on the surface of water and will travel outwards. Place a cork at some distance from the dipping of pencil. When waves reaches the cork, it will move up and down along with the motion of water particles by getting energy from the waves. This activity shows that water waves, like other waves, transfer energy from one place to another place without transferring matter. Water, that is water. Definition: waves, a traveling disturbance that carries energy through water, through matter and space. Waves transfer energy without transferring matter. Waves are produced when something vibrates. So this is about wave. Now, different terms related to wave. Crest, highest point on a wave. This region is called crest. This region is called crest. This is above this line. The region above this line is called crest. This is called trough. The region below the line is called trough. Node. This point is called node. The point at which amplitude is zero is called node. At this point, the amplitude is zero is called node. And at this point, the amplitude is maximum. The amplitude is maximum at this point and at this point. So it is called antinode. Wavelength, distance between crest and trough. This is the distance between two node or two antinode is called wavelength. If you take this, after which the wave repeat itself. After this, the wave will repeat itself. So this distance is called wavelength. Frequency. How many waves hit a certain point in every second? The number of vibration completed in 1 second. Number of vibration completed in 1 second is called frequency. Now, if you look to this diagram, this is the depth of ocean. So here the depth is more, amplitude of the wave will be smaller, wavelength will be larger, speed will be high. So in the mid of ocean, or simply say in the mid of sea, waves will have high amplitude, will have high speed, low amplitude, high wavelength, and high speed because the depth is more. Here, the depth is reduced. So amplitude increases, wavelength decreases, waves get slower, speed decreases. So if there is destruction more at the coastal areas, it is because of longer amplitude. So crest is the region above the mean line. Trough is the region below the mean line. Node is the point at which the amplitude is 0. Antinode is the point at which amplitude is maximum. So thank you, students. Do revise. In next week, you will get your homework assignment. This is your first week, so enjoy your liberty. Thank you, students. Allah Hafiz.